All right, so once again, this whole section's all about aromatic compounds. And before we get into any of the other stuff here, I just want to get nomenclature out of the way. So the thing about the nomenclature here is we have a bunch of different parent molecules now. So it turns out that if you have just benzene, that is the parent, so we can call that benzene. But if you have any other groups on there, these types that we're going to show here in a moment, you need to name the parent differently. So this is, be thorough here, this is benzene. If we add a methyl group to it, fix my lead in my pencil. This becomes toluene now. So if we had a different group on here, like a bromine on there somewhere, I would call that a bromotoluene rather than a methyl bromobenzene. So once again, we're going to give priority to these parent names first, over just using benzene. So once again, if I had a bromine on here somewhere, I would call it a bromotoluene versus calling it a bromomethylbenzene. So naming it with this as the parent is the more correct way. We have a couple other ones we've seen. We have our phenol, OH. So that's phenol. So I got a question for you guys. See if you can figure it out. Suppose I had a methyl group on this phenol. Would I name it as a phenol or a toluene, do you think? You would name it as a phenol because we give priority to oxygen groups, right? So if you have an OH on there, you're going to name it as a phenol. All right, for the rest of these, I'm going to go ahead and abbreviate the ring as pH just to save some time here. And I want you guys to know these. This one here is aniline. We have this one we've seen before last semester. This is, you guys remember what this one is? If it has a carboxylic acid. This is benzoic acid. We used that last semester during the acid-base lab. All right, moving along here, if we have a methyl ketone, like that, that is acetophenone. I do want to point out something here. If you have a carbonyl methyl, often referred to as a methyl ketone, that's also an acetyl group. So you're going to see that in the naming here. That's where the aceto comes from. So we have one side of the acetyl group. We have the phenol. It's a ketone, acetophenone. All right, moving along here. If we have an OCH3, this is anisole. Anisole. And then we have our xylenes. These basically have two methyl groups on there somewhere. And then the last one I want you guys to know is if we have a double bond coming off like that, that is styrene. Okay. Before we can do some practice problems, I have to show you about how we work the numbering if we have a di-substituted benzene. So di-substituted benzenes. If there's only two groups on there, we don't typically use the numbers. We're going to use a different type of prefix here. And there's only three possible situations. So let's go ahead and draw three benzenes, and then we'll take a look at the different variations. All right, so one situation is where we have that. The other one is where we have that. And then the last case is like that. This is only for di-substituted benzenes. So it works out where this, if it's 1, 2, it's ortho. And we typically give it the prefix, just the lowercase o, then a dash in front of the name. The next one here is meta, M dash, And the last one here we saw a bunch during the NMR stuff. That is para. Like that. You may remember we had that one compound, the MCPBA. The M in MCPBA is actually for the word meta. So that was meta perchlorobenzoic acid. All right, let's go ahead and just do a few practice ones here just so you're okay with it. So I had that example I mentioned earlier to you guys. If we had a methyl and an OH, you have to decide what the parent is. You essentially want to give priority to heteroatoms. So this is a phenol as the parent. And is that ortho, meta, or para? It's meta substituted, so I would call this meta-methyl phenol. So M-methyl phenol. All right, let's go ahead and try another one. So what if we have that? So am I gonna? Yep, you're right. So I did mention back when we went over alcohol nomenclature that if you have a non-alcohol oxygen group, it's typically priority. And in this case here, we have a carboxylic acid group versus an alcohol. So you want to give the priority to the carboxylic acid group, meaning the OH is named as a hydroxy, not as an alcohol. So this is para-hydroxy benzoic acid. So para-hydroxy benzoic acid. Running out of room here. All right, let's go ahead and let's do one more for this. Well, I want to do two more, rather. So let's go ahead and do that. And what else do I want to put on here? Let's put a bromine. Go ahead.
So for the names that you have where it has a phenol group attached to things, that means there's an alcohol sitting out, right? They're all phenols.
You mean for this one?
Above that, when you were getting the compounds.
These names?
Yeah, so all those phenol groups have an alcohol sitting out there, right?
No. Phenol is specifically you have an OH. These are just benzene compounds. Yeah, pH stands for phenyl. Yeah, YL. So that means a benzene ring. Yeah, just so we're clear, guys, just want to clarify here. If you see me use the symbol pH, that is a benzene ring. It's just a shorthand for it. I will tend to draw it out because it's usually relevant to draw it out, but yeah, in general, that's just a benzene ring. All right, going back to this problem here. The parent, what is the parent on that one? That's an aniline. And then what is the prefix I use on that? That's ortho. So ortho, bromo, aniline. All right, let's go ahead and just do one more for you guys. All right, I want to go ahead and put a methyl here. And then NO2s. Okay. These are all NO2 groups coming off. Was that one of the common parent? No. So basically, we're just going to call them nitro groups, like we would before. So no new names for here. They're just nitro groups. So we have a trinitro, and then what is the parent? So is that just benzene as the parent? Is it toluene? That's toluene, yeah. So the parent is toluene here. So I'm going to call the, so now we have more than two groups. We can, it no longer makes sense to use ortho, meta, para. You have to just fall back to your numbering. And the way you want to go with this is that whatever group is defining your parent, call that carbon 1. So typically you want to give priority to heteroatoms, but in this case, we're going to give priority to the methyl group here because that's part of the parent name. So I'm going to call this a 2, 4, 6 trinitrotoluene. So 2, 4, 6 trinitrotoluene. And this has a common name of TNT. Dynamite. Gotta do that. Can't resist. Yep. I believe the first Nobel Peace Prize was given for the person who created trinitrotoluene, right? Yeah, we're going to actually see why that's significant in this chapter, because it's actually very difficult to make this by the chemistry we cover in this class. The method he had to use had to be different. It turns out that as you put nitro groups on there, it becomes increasingly less reactive as you add more nitro. So getting that third one on there, not sure how you do that. But yeah, getting 2 on there is reasonable, but the third one is very challenging. All right, let's go ahead and switch over to heats of hydrogenation. That's before we start the chemistry, actual reactions. I would not write on that yet. Yeah, you'll see why. I haven't started using it yet. You shouldn't start using it yet. So most of that's actually going to be next time's lecture. I do have extras. I printed out a bunch of copies. I am not giving templates on the test, though, so you need to know how to draw benzenes on your own. So you should not need the template. Yeah. Unless you have one of the little templates already, right? I know some of you guys have those already. All right, let's go over heats of hydrogenation. Do you guys remember what the word hydrogenation means? Was that a reaction we covered before? That was addition of H2, right? So we're specifically talking about the reaction of H2 palladium on carbon reacting with a pi bond, essentially. So basically what people have done with this here is we can see how resonance of pi bonds has an impact on stability by looking at comparative heats of hydrogenation. So I have a couple things here to take a look at. So we have a standard cyclohexene. We have one here that has the double bonds and conjugation. And then we have the last one, which has 3 double bonds and conjugation as well. So that's our benzene here. All of these are reacting with H2 and palladium. So H2, 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 and then they're all going to give us the same product. Getting our hexagon practice today. Like that. All right, so essentially the way this works is they'll look at the first reaction as like the basis of comparison, and then they'll look at the actual heat of hydrogenations for these reactions and they compare them. And they were found to be different. All right, so this one here worked out to be minus 120 kilojoules per mole. All right, so by comparison, you would think that, okay, since I have 2 of these double bonds, that should have a value of negative 240 because we have 2 double bonds. It just makes sense that way, to think that way. But it turns out that it's a little bit different. It is 232 kilojoules per mole. And what that means is that the 8 kilojoule per mole difference is due to the additional stability from having the double bond and conjugation. So 8 kilojoule per mole due to conjugation. That's additional stability. This is typically how we talk about stability with these kinds of compounds. However, if you had the double bonds outside of conjugation, like they were across the molecule from each other, they should be equal to minus 240 because they're not in conjugation with each other. Basically what I mean is if they were isolated, they should work out to be exactly twice that value. All right, the next one here, because the compound is now aromatic, this is pretty different here. It is minus 208 kilojoules. All right, let's do a little bit of math here. So if it was just standalone, like a trialkene or triene, it should be what, minus 360? So what's the difference here? That 152 difference? And that's kilojoules per mole. And this is due to aromaticity. So look how much different that is compared to just a standard conjugation. That's a pretty big difference there. And that's due to aromaticity. All right. So once again, here to summarize, we take a look at the heats of hydrogenation for a standalone reaction here. And then we start looking at the ones that are in conjugation and then comparing them as if they were isolated versus what they actually are. And whatever that difference in energy is additional stability due to conjugation and or aromaticity. Are there any questions about this concept so far? Okay, the main thing you're going to have to do with this section, besides all the benzene reactions, is to take a look at a compound that is not benzene and be able to predict whether or not it's aromatic or not. So far in this class, we pretty much just lumped all benzene compounds and aromatics. It turns out that aromatic compounds are a whole class of compounds, not just benzene. So we got to take a look at this. So this next section, we're going to go ahead and call it Aromaticity and Huckel's rule. Or I think that should pronounce Huckel's. See if you guys can help me with this. I've been debating this for quite a while now, how this is pronounced. So Aromaticity and Huckel's rule. And this, they have the U with the funny dots on the top. So, is that Huckel? No? Is that right? I don't know. I'm just guessing here. And this is the so-called 4n plus 2 rule. I do want to point out that a lot of textbooks like to do a molecular orbital discussion about this. I do not do that. Huckel's rule is consistent with those molecular orbital discussions. So if you see all the little orbital diagrams in your book, I'm not testing you on that. I'm going to be testing if you know how to predict aromaticity from Huckel's rule. All right, so the conditions for a compound to be aromatic, so we say that it's aromatic if all the criteria must be met here. So the molecule must be planar. This is the first one. Molecule must be planar. If you think about this back to what we did last time, if the molecule is planar, that allows all the pi bonds or all the pi orbitals to be in conjugation. So adding a little note to this one, all p orbitals are parallel in conjugation. If you're not sure what I'm talking about, I did draw out the allylic carbocation last time, and that showed that these are all parallel to each other. Imagine that around the whole ring now. All right, another rule here, it must have a continuous pi system. Meaning that there's no breaks in it, so if you have an sp3 carbon in the middle of this ring, it cannot be aromatic because you cannot push molecules or electrons through the sp3 carbon. And then if you also have an sp3 carbon in there, you have the situation where it's no longer planar, right? So these are typically going to be sp2 hybridized due to the planar molecule. All right, the last part here is where the Huckel's rule comes in. It must have exactly 4n plus 2 electrons in resonance. You're going to get a full 360-degree resonance here, it must have exactly 4n plus 2 electrons. So 4n plus 2 electrons in resonance around the ring. And when I mean around the ring, it means a full 360 degrees like we see with benzene. So full 360 degrees. Some people like to call these so-called magic numbers, meaning these are your numbers that you're going to have for pi electrons. And I want to just emphasize here, these are pi electrons in resonance. So if n is equal to 0, what do we have? It's 2. So it essentially works out where it's every other even number. So 2, 6, 10, 14, etc. to infinity. It works out where if the molecule has a non-magic number, nature does not like that. It ends up being a bond order thing. Or doing bond order back in Gen Chem, maybe. You end up getting a bond order of 0 if you have non-magic numbers. So that's where the molecular orbital discussion comes in. I want you guys just to recognize magic numbers versus non-magic numbers. So non-magic numbers are 4, 8, 12, etc. If it has a non-magic number, we usually refer to those as being anti-aromatic. Anti-aromatic. So once again here, what nature will do, because nature does not like this setup with anti-aromatic compounds, they're very high energy. What it'll do is it'll distort the molecule to make it bent, so it's no longer planar. It no longer has to deal with these aromatic or trying to be aromatic anymore. It'll be basically treated as standalone alkenes at that point. All right, so what you're going to have to do in this section here, if you've seen the worksheet already, is if you're given a bunch of different compounds, you have to identify them as being aromatic, anti-aromatic, or non-aromatic. And I'll go ahead and do an example of each here. So this compound here, notice how I have an sp3 carbon here. So if you were to try to draw resonance for this, you would not be able to get a full 360 because of that carbon right there being sp3 hybridized. So I would say that this one is non-aromatic. It's not planar. So non-aromatic. And I want you guys to be clear here. I'm going to be picky versus non versus anti. They mean different things. The other case here is where we deprotonate and put a negative charge there, like that. And just so we're practicing I want to do some resonance practice here too, to further illustrate the full 360 resonance that we're going to see. All right, so boom, like that. We're going to have to 2 arrow pushes at once here. All right, new lone pair is there. Double bond is now here, like so. And then you basically keep doing this over and over and over until we get back to our starting point. You should be able to get back to your starting point at some point. I've noticed just working with these over the years, you tend to go around the ring twice before you actually get back to your starting point if you're practicing these. You probably want to practice these. All right, keep moving along here. So it looks like a new pi bond there, negative. And then I think we got to do 2 more to get back to our starting point. So that goes there, like so. Notice I'm using the resonance arrow here, not an equilibrium arrow. So lone pair is now here. Double bond, and then 1 more will bring us back to our starting point. So if you're able to do this kind of resonance where you go around the full 360, you get back to your starting point, and you have a magic number of pi electrons you're moving around, the compound is aromatic. So we have a lot of conditions here that must be met. Right, back to start. So if we want to take a look at the resonance hybrid, oftentimes the resonance hybrid for aromatic compounds is able to just draw the ring here and just put a circle in it. You probably seen benzene drawn that way, right? Where they just put a circle in it, like that. And because this one has a charge in it, I'm going to put a negative in there. All right, so now the question is this compound aromatic? So you look at, think about all the electrons that are possibly moving here. So looking at our first structure here, we have 2 pi bonds, 1 lone pair. That's 6 electrons total. That satisfies the criteria for Huckel's rule. This is aromatic. Okay, and then the reverse case here, where instead of a negative charge, we put a positive charge there now, like that. I don't want to do the resonance for this right now, but I just want to mention that it will end up looking like this. If you did the whole resonance for it, it goes around the whole ring. So this had 6 pi electrons, and then what about this one? Is that aromatic? So we don't say non-aromatic, we say anti-aromatic is the word we use. So this one is anti-aromatic. And that because it has the non-magic number. So essentially what happens is you want to use non-aromatic if it just doesn't meet the criteria at all. So you can't do resonance here. So pretty much all the straight chain compounds we talked about all year long, those are all in the category of non-aromatic. It's usually between aromatic and anti-aromatic where you have to make the distinction with Huckel's rule. Okay, I have a few more examples here. And let's go ahead and see what they are. So first example here, I'm going to set this here. What about this compound? So I got a 3-membered ring with a double bond and a plus charge. Is that compound aromatic? So how many pi electrons? 2? Could you do a full 360 rotation in resonance here? Yes? This is aromatic. Yep, this compound is aromatic. So aromatic. And once again here we have 2 pi electrons in resonance. All right, and then another one here is, this is add the negative charge there now. And then we have one where we don't have the charge at all. You can get 3 different variations here again. This next one here, if you were to do the full resonance here, you'd end up moving 2 sets of pi electrons around. That's anti-aromatic now. So this one is anti-aromatic. That's because we have a non-magic number of 4 pi electrons. And then this last one here has 2 hydrogens right here. We cannot do resonance through that carbon. That makes it non-aromatic. Are you guys seeing the distinction here between them? So just to be clear here, I am going to be particular on the wording on this. So aromatic, anti-aromatic, non-aromatic. All right, let's go ahead and take a look at another one. So here I have a stop sign. Looks like a stop sign to me anyway. That. What do you guys think? Is it anti or non? It's anti. Yep, and the reason why is because we do have the full pi system here. There's no sp3 carbon. So basically the tell is the sp3 carbon is for non-aromatic. So this one is anti-aromatic. Nature does not like this, so what nature will do, it'll actually curl the molecule where you would expect it to be planar, but the curl is happening because it wants to get rid of this anti-aromaticity. It is not favored. What's that?
Oh, is it 8?
Yeah, 8 pi electrons here. Yep. So 8 pi electrons, that is a non-magic number that ends up being anti-aromatic. All right, a few other things I want to talk about before actually starting into some of the reactions. We'll see how much time we have today. Is you may have heard this term before for anybody that's into anything environmental. May have heard PAHs. This stands for Polycyclic Aromatic Hydrocarbons. Yep. So polycyclic aromatic hydrocarbons. These are a pretty big concern in the environment. They are fairly toxic to most things out there. And essentially what we have here is they're fused compounds. So here, I think you may have seen this one before, probably last semester or freshman chemistry. We use this compound also during the pre-point depression lab in chemistry 121. But this compound here is naphthalene. It is a PAH. So naphthalene, is it aromatic? Yep. Yeah, you essentially have two benzenes fused there together, and if you're following Huckel's rule, it is consistent with Huckel's rule as well. A few other examples I have here for you is if you have three put together, and just for the sake of discussion, I'm just going to put circles in them now. This is anthracene. A little side note about naphthalene, if you ever smelled the smell of mothballs, you're smelled of naphthalene before. That's what that smell is. The next one I want to mention here was actually part of my graduate research. It turns out that this compound is actually a unique chemical tracer for burning coal. So if you burn coal, this compound does come off. It's a PAH. You know, you got that clean coal, right? So, sorry, couldn't resist. So 5 rings together, this is piscine. It is a common combustion product from charcoal when you burn coal, and it turns out that no other organics known to man give this compound off when they're burned. So we use it as a unique marker for coal burning. All right, another one I want to mention here before we move on here is heterocyclic aromatics. These are the fun ones. So heterocyclic aromatics. These are basically ones that have a heteroatom embedded in the ring. So they're not coming off the ring, they're a part of the ring, and they're often part of the resonance, if there is resonance in it. But we'll see here. Okay, so a couple examples I have for you guys. The big one we've seen so far is if nitrogen's in the ring, and it's a 6-membered ring. This is, remember what that one is? You should have seen it in your studying. It's been used as a solvent a couple times all year long as well. It's literally the P in PCC. it's pyridine. Yeah, pyridinium is the conjugate acid of it, but this is pyridine. All right, a few other ones I have for you guys are if you take one of the carbons out. I'm going to throw the lone pair in there. And this is perol, LE. And then the other ones here, if you put some oxygens in there. You guys have, we've seen the hydrogenated version of this. So this compound is furan. If you hydrogenate, you add 4 hydrogens to it, that becomes tetrahydrofuran, which is that THF solvent. And then next we have the Superman molecule. It's not actually what it's called, but it looks like Superman symbol to me a little bit. This is thiophene. Now the interesting thing about this, it turns out, I work with thiophene compounds quite a bit during my graduate work as well. And it turns out that thiophenes are actually unique markers for burning diesel fuel. So a lot of the sulfur content in your fuels are thiophenic in nature, meaning that they have this kind of ring in it. And it turns out that dibenzothiophenone is actually a unique marker for burning diesel fuel. All right. So when determining aromaticity, you only count the lone pair towards the magic number if that lone pair is part of the resonance. So I'm going to add that comment here. Only count lone pairs on heteroatoms if they are part of the resonance. So I take a look at these compounds and think about, okay, am I going to have to move some lone pairs here to get the full 360 resonance? So what about the first one? Pyridine. Do I need to use that lone pair nitrogen to get the aromatic resonance here? You don't actually need it. It's just like benzene now, right? So you can do the full 360 here. Let me show that down below here. So we can draw resonance. We can go ahead and do all three at once, just like benzene. Boom. And I can do this without touching that lone pair at all. So when we take a look at whether it's aromatic or anti-aromatic, you don't include that. Only the ones that you have to actually move. Like that. So I would say that this has 6 pi electrons. It's aromatic. All right. What about parole? You have to include that lone pair to get the resonance here. So in order to, we have 6 pi electrons there, so parole is also aromatic. So now I have the additional question that I want to ask here. Which nitrogen is more basic out of these two? So would you expect pyridine to be more basic or parole to be more basic? Why is pyridine more basic? No. Any ideas? So essentially, if lone pairs are involved in resonance for aromaticity, they're typically not available for acid-base reactions. So in this one here, we had to include we don't include the lone pair that's available to go grab an H or something. Where this one here, that lone pair is part of the aromatic resonance, it's not available. So I would say that this one is a stronger base, weaker base. Just a little heads up on some acid-base stuff that we're going to be seeing. So once again here, this is a stronger base. And the reason why is because the lone pair for this one is not involved in the aromatic resonance, where this one it is. If you think about it here, what's going to happen if this compound were to grab an H? Let's go ahead and show that. So the next page, let's look at parole. So put an H there, lone pair. You could show the resonance for this, but I just want to go ahead and do the acid-base reaction. So grab an H, boom, and then take a look. I would say that this reaction is not favored at all. And the reason why is because you are losing aromaticity. So now the question, we lost aromaticity here. Is it now anti-aromatic or non-aromatic? So this one is aromatic. What is the product? Is it non or anti? It's non. Yep. Non-aromatic. The tell for that is the hybridization on nitrogen here. It's now sp3. You cannot do resonance with an sp3 atom like that. If you were to push electrons towards that plus charge, you'd have to break a bond to prevent from violating the octet rule. All right. So the kind of thing that I would ask you guys here, is a compound aromatic or not? I could do a nomenclature question potentially. And the other thing I like to do is if I give you a compound that has a couple nitrogens in it, you have to rank them by increasing order of basicity. And this is a big thing here, is if the lone pair is part of resonance. I probably won't do something too crazy till we get to the amine chapter, but you may see something like this simple on a test or a quiz coming up. All right, I want to go ahead and switch gears here a little bit. We are now officially done with the aromatic section, just for identifying what aromatic compounds are. And then the remainder of today is going to be going over aromatic reactions. And that's pretty much the end of or all the way till the exam. When is our exam in this class next? Next week. Oh my goodness. So it's pretty much just going to be all the conjugated pi systems on there. So it's going to be dienes and aromatics. I think that's going to be more than enough for one test, though. All right, so let's take a look at our aromatic reaction.